So hello and welcome back. In this video we want to do example number 4 on page 469, and the question is: in 2006 80 deer were introduced into a wildlife refuge. So in 2006 basically 80 deer were introduced into this wildlife refuge. By 2012, the population had grown to 180 deer. So by 2012, the population had grown to 180 deer. And the population was growing exponentially. So this is another piece of information, exponential. This is an exponential growth. That means we can use an exponential model for this population of deer. So write an algebraic function n of t representing the population of the deer over time t. So when you want to solve this kind of problem, basically you have to basically write an equation for this function. An exponential function is always in the form f of x is equal to a times b raised to the power x. So you know that your a is the initial value. I can take 80 as my initial value because that's when the population was first introduced into this wildlife refuge. And then, so I can take 80 as my initial value. Next, I don't know what my b is because I do not know what my growth factor is. So my growth factor is basically if I had some sort of function, for example, if they told me that, for example, in 2006, something like this. If they told me that this is, let's say t, this is n of t. If they told me that in 2006, for example, the population of deer was 80, and in 2000, for example, in 2007, the population was 80 times 1.6, and then in 2008, it was 80 times 1.6 times 1.6. So this way I can conclude that my growth factor was 1.6 because every time I added 1 to my input, the output was multiplied by 1.6 one time and another time and the other time, and so it just keeps on being multiplied by 1.6 as I'm increasing the value of my input. But here I just don't know what's going on because in 2006 it's been 80, in 2012 it's 180. In 2006 it's 80, in 2012 it's 180. So 6 years have passed here. So this is 6 years, and during this 6 years, the population has grown from 80 to 180, but there is no way to know what was happening in between. So what I can do here, basically I know that my a is equal to 80. I know that my a is equal to 80. So, and I have basically one piece of information that I can use here. I can basically take this year 2006 and as 0. So I could basically do this table. And this is t, this is n of t. This is 2006, which was 80 deer. This is, let's say, 2012, which was 180 deer. So I can take 2006 as year 0 years after 2006, and then based on that I can take 2012 as year 6 years after 2006. So then I have basically 2 points on the graph of this function. One is this point, which is the t is 0 and n of t is equal to 80, and the other point is t here is equal to 6 and n of t is equal to 180. So I could use one of these points, and let's see how we can use that. So basically your function is going to be something like this. So I can use, for example, this point over here. This would be easier, but now let's use this one. So f of x here is equal to 180, is equal to a, which is basically 80, times b raised to the power 6. So here what you can do is you can multiply both sides of this equation by 10, which will, this makes this 18, makes this 8. So basically 18 is equal to 8 b raised to the power 6, and I can rewrite this as b raised to the power 6 is equal to 18 by 8. So this divided by 2 is 9, this divided by 2 is 4. So b raised to the power 6 is equal to 9 by 4. So that basically means that b, or I could take the 6th root of both sides of this equation, which would give me probably some answer. So the 6th root of b raised to the power 6 is equal to the 6th root of 9 by 4. And let me calculate this here. So this becomes b, and the 6th root of 9 by 4 is, let me see. So basically the 6th root of 9 by 4, it turns out that it's I take basically 4 decimal places, so it's 1.1. Let me see. 1.1447. 447. Of course, this is supposed to be approximately equal to, but well, we can just assume that we have rounded up to 4 decimal places, so it could be an equal to as well, as long as we know what we've done. So let's see if that works. Let me see if that works. So basically, if a is equal to 80, b is equal to 1.1447, we could assume that n of t is equal to 80 times, because this is my a times, it's supposed to be in the form f of x is equal to a times b raised to the power x. So a is basically 80, b is 1.1447 into raised to the power t. Now there is no way to know. It seems that it's right. Now you can test it, of course. For example, you can calculate, I don't know, f of, or n of 0. N of 0 here is equal to 80 times 1.1447 raised to the power 0. This becomes 1, so this is equal to 80, and this is your output here. And let me do the graph of the function as well, and test the function over there as well. Well, I tried so many graphing calculators online, and Of course, all of the graphing calculators that I do have are PC based or online, but none of them could plot this function, because this seems to be a complicated function. But anyway, it's now this is the graph of this function, and the equation that we got for the function is basically this equation, 80 times 1.1447 raised to the power t, which is the same thing that basically the book has also represented for this function. And I don't know how they've done this, but of course it's easy. If you're sure that basically you have 2 points, and they have basically used some sort of technology to graph this function, and you can see that the graph passes through these 2 points, 0, 80, the initial point, and also this point 6, 180, which was after 6 years in 2012. And of course, you basically, it seems that since this is some sort of exponential function, exponential functions, as you know, get too large after a short period of time. So if you actually want to use this model for an actual population of deer, then you have to somehow limit the domain of the function so that it can be realistic and useful in real life situations. But the goal of this exercise was to be able to write this, to come up with this formula, and we did that. So again, another thing that you can see here, the domain goes from 0 to infinity, the range goes from 80 to infinity, and that's it. That's basically how you do this kind of function. So basically, in every situation, you just need to use your logic, see what you already have, what sort of information has already been given to you, and then based on that, somehow try to find the variables or the things that you don't have in order to write the equation of the function. So in the next video, we might do this wolf population. And I'll see you in the next video.